My title is the gravitational index of the heterotic string, and by index I mean the supersymmetric index. Most people are familiar with this here, but the full title may not be self-explanatory, so I'll spend the first 10 minutes or so trying to explain this. And because we have only half an hour, I'll just jump into the main question. So here's the context. Consider a supersymmetric compactification of heterotic string theory, okay, where the compactification manifold has at least one circle. In order to be concrete and simple, in this talk we'll just take heterotic strings on T6, the 6 torus, and consider a fundamental heterotic string that winds this circle W times and carries some momentum N around the circle. Okay, so there are two charges, and then we set the right moving oscillators to their ground states, and because the supercharges of the heterotic string arise from the right movers, this string configuration preserves half of the 16 supersymmetries of the theory, and the mass is determined by the right moving momentum. Okay, this is all basic stuff. But the left movers can be excited to arbitrarily high energies, and so you have an infinite tower of BPS states. Okay, this was studied by Dabholkar and Harvey. And this tower of states has a Hagedorn growth that's fairly easy to calculate. The asymptotic degeneracy of states goes as exponential 4 pi square root of NW for this T6 compactification. And the question we want to ask is, what happens to this tower of states when the string coupling is large? So this description was the free string or weakly coupled string. And now because it's a supersymmetric compactification, we take G string to be large in the gravitational regime, and the question is, what's the description? Okay, so this question was asked by Ashok back in '95, and there's a lot of discussion here. The string black hole transition due to Susskind and Horowitz-Polchinski. I want to postpone all that to the end of the talk. But I do want to comment that the same question asked for the 3-charge system, the D1, D5, P system, a year later led to the famous breakthrough of Strom and Javafra. It was the first microstate counting of black holes in string theory. But this original question of the 2-charge heterotic string, I think it's fair to say, is still not settled. Okay, so let's briefly discuss why that's the case. So there's some exponential growth. So the first guess is that the gravitational dual is a black hole, and because the states are supersymmetric, so is the black hole, and typically supersymmetric black holes are extremal, so you might look for extremal black holes. It's fairly easy to write down a solution in 2-derivative supergravity. There are 2 charges, you write 2 harmonic functions, and immediately you find that this solution is singular. The horizon is on top of the singularity. So the next step is that this singularity could be resolved by higher derivative effects in the effective Lagrangian in string theory, which are suppressed by the string length. So the horizon now will be not on top of the singularity, but string scale. Now this is a hard problem because higher derivative effects are complicated. And progress has been made assuming that there is symmetry enhancement at the horizon, near the horizon of the black hole, okay, which is usually the case for supersymmetric black holes. So if you assume that this 4-dimensional configuration is ADS2 times S2 times a T6 with 16 supercharges, all the symmetries and supersymmetries are enhanced, then the tensor structures simplify and one can make progress. Okay, so there's been quite some work in that direction. People here in the audience as well. However, there's a problem with this, which is that, as far as I know, there's no known solution in supergravity which agrees with this, ADS2 times S2 times T6 with 16 supercharges. Okay? You can make this a little more formal. You can say, you can try to look for symmetries, and because there's an ADS2, there's a conformal group, so you can look for the list of superconformal groups. And there's no superconformal group whose symmetries agrees exactly with this, with 16 supercharges. Now, this is not a proof. Maybe things go here and there, something might give. But I want to cast doubt on the existence of this extremal black hole. Okay? So this is sort of a symmetry problem, a kinematic problem. There's also a dynamical problem, namely that there is another solution which is known by Horowitz and Polchinski with the same charges in the gravitational regime. It's called the self-gravitating string gas, which is triggered by the fact that in the Euclidean theory, there's a thermal circle and there's a certain winding mode of the heterotic string. When the circle becomes small enough, this mode becomes nearly massless, and that can condense, and the solution involves such a condensate. And in recent work by Chen, Mallison, and Witten, so they generalized this to a large class of solutions with charges being that of the heterotic string, and they argued that near extremal states of the fundamental heterotic string are likely to transition here. Okay, so more precisely, you take this two-charged black hole and also give it a lot of energy, so make it non-supersymmetric, non-extremal. That's a perfectly well-defined black hole solution. It's regular. Then you reduce the energy, the mass, to the BPS mass, or extremal mass, and that's what happens. Now, of course, it's not really under control, but you can extrapolate and you can study the thermodynamics. And the conclusion here was the thermodynamics seems to suggest that, in fact, you go to some solution of this type. Okay? Now, again, I'm happy to discuss more about this in the after the talk. But what I want to do is a slightly different. So I want to approach this problem from a different angle, not as a limit of near extremal states. Just ask directly, there's an ensemble of supersymmetric states, what's the gravitational description? Okay? So I want to use supersymmetry. And in particular, to do that, I want to focus on an observable which gets contributions only from supersymmetric states. Okay? And then ask, what's the gravitational interpretation of that? Now we have such an observable at hand for a very long time, namely the supersymmetric index. And this is where I want to take the talk, so I just want to change the mood a bit. So I'll just go through some basics. So take any quantum system with one complex supercharge. With this algebra, QQ bar is H. And you can construct the Witten index, trace minus 1 to the F, e to the minus beta H. Maybe I move this side, it's easier. And in order to define this trace for convergence, you need a non-zero beta, because there's a tower of states. But as we know, because of the pairing of bosons and fermions, this trace is independent of beta, and it's equal to the number of bosons minus fermions at zero energies. Those are the supersymmetric states in this problem. And because of this pairing, this index is also invariant under supersymmetric deformations of the Hamiltonian. Okay? So in this case, the supersymmetric states that were counted had zero energy. And if you want to apply this to black holes, we want to look at supersymmetric states which have mass. So we need to do something slightly more sophisticated. So you consider some slightly more sophisticated index. So the context is n equal to 2 supergravity. This has 8 supercharges. You take one complex supercharge such that QQ bar anticommutator is the E minus the BPS mass. So you work in a fixed charge sector. There's a definition of BPS mass, and that's the anticommutator. Okay. And the index under consideration is called the helicity supertrace. It looks essentially like the Witten index, but there are also some there are fermion zero modes in the problem because the states are not individual states but multiplets. You have to absorb that. I'm not writing all of that. Essentially, it looks like a Witten index. Okay. So you have trace minus 1 to the F. Now E is QQ bar plus MBPS. And now you see that this part of the trace here is really a Witten index of the states with charge Q, and that index I'll call D micro. Right? For this two-charge system, so this can be calculated in any free theory. For this two-charge system, you can calculate it, and the answer is exactly this growth that we saw, e to the 4 pi square root of NW, with some prefactor which is not visible asymptotically. Right? Good. Now, the question is, what is the interpretation of this in the gravitational theory? Right? And I stress that this is not just some intellectual curiosity. In all microstate counting problems in string theory, one is not actually counting the number of states. We always calculate some index of this type, either of this type in supergravity or in superconformal indices or something of this sort. Okay, so if you really want to follow sort of, what string theory is telling us, we have to answer this question. Okay. So, well, so we can write this index in the gravitational variables. Okay. We don't know how to write trace in gravity, but we can write a path integral formally So it's an integral over all the bosonic fields and the fermionic fields of supergravity with some effective action, which contains all kinds of stringy modes. Okay, this is how we would imagine the path integral. Right. Now this is the space-time. This is Euclidean space with a circle, thermal circle of radius beta, and all the fields are periodic, including the fermions, and that's what implements the -1 to the f. Okay. So this is the dual to the Witten index that, or this index, supersymmetric index that we construct. All right. Now this is a formal integral. I'm not going to solve any UV problems of the definition of this path integral, but it's a good question to ask: what is the saddle point of this integral? All right. Now the fact that the entropy of the black hole agrees with this index so well in so many situations might lead you to think that the saddle point is a supersymmetric black hole. Okay. However, if you think about it a little bit, that cannot be the case because, well, for a couple of reasons. So firstly, in gravity, so this is Euclidean path integral. So in gravity, a path integral looks, a black hole solution in the Euclidean theory looks something like this. There is a thermal circle, and then you fill it in, and this thermal circle contracts at the horizon, and that's the circle, that's the sphere, which is the Euclidean horizon. Okay, after that, there's a hole. However, supersymmetric or extremal black holes have zero temperature. Beta goes to infinity, and therefore, correspondingly, an infinite throat. It doesn't cap off. And if you try to sort of force it to fit a circle of size beta, you run into problems. Okay, you either get a singularity or the entropy of the configuration is zero. Okay. So that's one problem. The other problem is that this cigar-like topology admits only one smooth spin structure, namely the antiperiodic spin structure for fermions. But that's the opposite of what we would expect from supersymmetry. Okay, we want everything to be periodic. All right. So these are problems. I just want to make a parenthetical note that nevertheless, as we all know, there's been an enormous amount of progress starting from Sturm-Ingerwaffe in explaining the the black hole entropy in both the microscopic and gravitational regimes. And in the gravitational regime, the progress has been made by using some kind of a mixture of Hilbert space and path integral techniques. At asymptotic flat space, you use some Hilbert space intuition. Think of the black holes as particles, and then you go near horizon and use a path integral. That's roughly what has been done in all these years. And what we want to do, and there's been enormous progress, but what we want to do here is to sort of write a uniform path integral starting in asymptotic flat space, like Gibbons and Hawking. Right? Now, the resolution of this tension has been known for the last few years, 5 or 6 years, which is to replace this -1 to the f, to shift it into a bosonic problem. So imagine some R charge in the theory. R charge could be spin, angular momentum, or it could be some gauge R charge, anything that couples to fermion number. And then you shift that chemical potential by pi I, and that effectively implements -1 to the f. Okay, so asymptotically you have a circle around which there's this holonomy. Then you ask, is there a solution of this type? Okay, which is supersymmetric. And indeed, such solutions were found. So because you have a chemical potential for R charge, the solution also carries R charge because there's condensation. They're complex. This is slightly funny. And you can see that they're complex in one way or the other. Something becomes complex. You can see that a sign of that, there's an I there. And the action, so these admit killing spinners. And the action of the on-shell action of this configuration, the Gibbons-Hawking free energy, it turns out to be independent of beta, as you would expect from the index. Okay, so this looks like a saddle point of the original problem. You have some Witten index of beta, and you want to ask what fills it in. Okay, so this was in this paper with Alejandro Cabo Bisset, Davide Cassani, and Dario Martelli in the context of ADS5 indices. So we were trying to ask what's the dual of the superconformal index in 4 dimensions. But then this was generalized to all kinds of ADS spaces, and then in this nice paper, also to asymptotically flat space. Okay, so this is what I want to focus on today. And here, so things take a particularly simple form. Okay, so firstly, asymptotically flat space means you're doing ungauged supergravity. There are no extra gauge fields. So the only R symmetry that you have is the spin, the angular momentum. So you must turn on an angular velocity. That's the chemical potential. And this supersymmetry relation turns out to be just simply this beta omega is 2 pi I. And you can see why that works in a very simple way. Gibbons and Hawking tell you that if you have a configuration like that with beta and omega, then the gravitational path integral calculates trace e to the minus beta h minus beta omega j. But this is 2 pi I, and e to the 2 pi I j is just minus 1 to the f. Okay, that's the main idea. All right. So this was in pure supergravity, that's Einstein-Maxwell theory. So what I want to do today is two things. So firstly, I want to lift this to a string theory embedding. So I want to discuss black holes of the type of Strom-Lindsay-Buffer, asymptotic flat space. In particular, I'll work with 4-dimensional black holes coming from type 2a compactifications on a Calabi-Yau. So the 4-dimensional effective theory is n equal to 2 supergravity coupled to vector and hypermultiplets. And in this setting, I want to describe these non-extremal but supersymmetric solutions. This is work with Jan Boru, Luca Elisiu, both here somewhere, and Joaquin Turiachi. And one thing, if you remember how things went, in the last 20, 25 years, in the gravitational, whenever you talk about these supersymmetric black holes, in the gravitational regime, the extremality is used, has been used crucially. So the starting point often is the attractor mechanism. Okay, so for attractor mechanism, you need an extremal black hole, and then you have a spherical horizon in 4 dimensions, all the scalars get fixed and so on. And now here I'm emphasizing that you should not have extremality. And so what we found in this paper was that there's a new version of the attractor mechanism. So the black hole horizon is not spherically symmetric, and the scalars are not quite fixed. Nevertheless, some things get fixed, and you can calculate. The entropy also has a strange, complicated expression. Nevertheless, the black hole free energy is defined, gives you the supersymmetric free energy. I'll explain all these things as we go. Okay, so that's the first thing I want to do. Now, the second thing is I want to do in a general situation, so not just for the heterotic system with which I motivated the talk, but for supersymmetric black holes in n equal to 2 supergravity. Okay? And then I want to specialize to this 2-charge heterotic system, and here one needs higher derivative, an extension of the new attractor mechanism to include higher derivative corrections, and this we did in this paper from February with Yiming Chen and Joaquin Turiachi. And there's a small surprise there, which is that including the prepotential terms from string theory gives you exactly the leading order entropy, including the numerical 4 pi. Okay? Yeah.
Is the fact that it's independent of beta, is that already an attractor mechanism? It's already surprising.
That's part of the attractor mechanism.
So even in Einstein-Maxwell, there's...
Yes. Yeah, exactly. So the new attractor mechanism is that the final free energy, the final entropy is the attractor, the extremal entropy, as you would expect. It's independent of beta, it's independent of the moduli, okay, and all these are highly non-trivial. Okay. So if you measure the area of the black hole that I'm talking about, it depends on the temperature and the moduli, but the final free energy does not. I'll explain this. Any other questions? It's a good time to take them. Okay. So let me go on to describe these two things. Good. So the context is n equal to 2 supergravity. Let me just remind you briefly what that is. So there's 8 supercharges in the theory. It's a 4-dimensional theory. So there's a graviton multiplet coupled to vector multiplets. Okay, hypermultiplets typically don't participate in such solutions. And there's some bunch of vector multiplets. Each vector multiplet carries a gauge field, a complex scalar which I'll call y, and some gaugini, which will not play a role in today's talk. And the black hole carries charge, electric and magnetic charges under all these gauge fields. The two derivative action is completely determined by one function called the prepotential that tells you how all these vector multiplets couple to each other and to the graviton. And that's a holomorphic homogeneous degree 2 function, okay, which here's an example. In the string theory compactifications that we're studying, that prepotential is just this cubic divided by linear, and is completely determined by the triple intersection numbers of the Calabi-Yau. Okay, so it's some microscopic data. And here these dots indicate that there can be higher derivative corrections to the theory. All right. Now, the general supersymmetric solutions to this theory has been studied a lot in the literature, and it looks like this. Okay. So you have a metric, scalars, and gauge field. So the metric has the following form. So there's a three-dimensional flat space, and then there's this time which is fibered over it. Okay. And this omega shows that there is rotation in the problem. Okay. So remember, rotation is the R symmetry, and these black holes that I'm discussing necessarily rotate. The whole solution is determined by a set of harmonic functions. You should think of these harmonic functions as being sources for the electric and magnetic fields. So there's twice the number of vector multiplets for electric and magnetic fields. So you see that this rotation one form is determined in terms of these harmonic functions, and this blackening factor is determined in terms of the scalars. GI is the first derivative of the prepotential, and the scalars themselves are determined by the harmonic functions. And the electromagnetic fields have a monopole field strength and a dipole field strength. Okay, that's one characteristic of these solutions. And in fact, a certain limit of this or specialization of this may be familiar to some of you. In pure supergravity, the same question, what's the most general supersymmetric solution, was asked in a very famous paper by Todd, and he found exactly the same type of metric. Pure supergravity means Einstein-Maxwell theory, there are no scalar fields. And this solution, this kind of metric, was actually known for a long time due to Perges and Israel Wilson. They're called IWP metrics. Of course, in the pure supergravity case, this just corresponds to the supersymmetric version, the supersymmetric limit of Kerr-Newman. Of course, that Lorentzian solution is not well defined. It has naked singularities. There's a ring-like singularity. But today, so we're going to weak rotate, and the Euclidean solution with a certain real slice is perfectly smooth and well defined. Okay. Now, so in order to specify a solution, we need to say what are the harmonic functions. And the harmonic functions in this case, so if you take all these harmonic functions and make them sources for electric and magnetic charges and put them all at one point, that gives you the extremal black hole. Okay? And in order to get this, so the extremal black hole, if you put them all at the same time, you have a double pole, the characteristic double pole of the extremal black hole. But what we're going to do is to resolve this into two sources, into the north and south pole, okay, which carry some charges. Okay? So P and Q are the monopole charges, and M and N are the dipole charges. Okay? So I'll just very briefly present what the data and what the solution is. So the boundary data are the following. So there's the monopole charges, which you fix from infinity, P and Q. That's the sum of the two charges. Okay? And then there's a temperature in this problem, or equivalently this angular velocity. They're related by this relation. And the solution has parameters. So the dipole charges are parameters because they die at infinity. You can't fix them at infinity. They die faster than 1 over r square. And then the size, the distance between the two centers, which by supersymmetry is related to the rotation or the spin of the problem. Okay, that's another parameter, real parameter. So there's as many charges as BPS equations, and then there is one more condition coming from demanding smoothness of the Euclidean theory. In Kerr-Newman, this smoothness is the usual smoothness constraint. You have a thermal circle, you want it to shrink. Sorry, you have a contractible circle, which is not thermal now because of rotation. You want it to shrink smoothly. But in this more general case, you can write the smoothness condition in this very elegant way in terms of symplectic inner products of supergravity. Okay, anyway, there's one condition which relates the distance to the temperature, and so there's as many equations as constraints. Yeah? So here we're in the Euclidean theory.
Right, but isn't that equivalent when I think of it from like this multi-centric configuration? So what's a condition that asks to not have
CTCs?
Yeah. From like the net more like solutions. Is that, and it looks like there was also a product between the charges. So
yeah, so this condition looks a lot like a certain condition which was present in Dennis' story, but there's no beta there. So the interpretation is completely different. There's no temperature in those solutions. Okay. Formally, there is If you remove the i's, formally it looks a lot like a certain equation arising in the Lorentzian theory. The interpretation is completely different. Okay, this really is from smoothness of the Euclidean solution. Maybe Luca or Jan has a comment. Jan?
Yes, so in Benjamin solution, we're studying the integrability conditions, and this is a condition in this language for having non-Dirac space in the configuration of like the gravitational direction. However, in this case, because we're in Euclidean series, we only require the Dirac fields are on coordinate singularities, and they are not parameter singularities.
So in that sense, formally it's the same, but the interpretation is different. Okay. So that's the solution, and now we want to talk about the entropy. So let me just recall some aspects of the old attractor mechanism, the classic attractor mechanism. So in 4 dimensions, the black hole horizon is spherically symmetric, and all the scalars get fixed at the horizon, and they're constant at the horizon. They're determined by the charges through these attractor equations, okay, famous attractor equations. This is beautiful work of Ferrara, Carlos, and Strominger. And now we don't have spherical symmetry. We only have a U1. So there's actually 2 fixed mark points. These are the 2 poles that I was discussing. And the scalars are not constant on the horizon. They depend on the angle. They also depend on the asymptotic moduli and the temperature. And the area of this black hole, the Bacon-Steinhagen formula, also depends on all of these, on the moduli and beta. Okay? However, near the poles, something nice happens, okay, which is that the scalars, so the y near the North Pole takes its extremo value, and y bar is 0. So here you can see that the solution is inherently complex. Okay? So y bar is not y star. And then at the South Pole, the opposite happens. Okay? So near the poles, you get back these nice algebraic equations. And then, as I said, the area itself doesn't have a nice form, but the on-shell action, the Gibbons-Hawking free energy, has nice properties. There are 2 nice properties. Firstly, if you take the Legendre, if you write the entropy as defined by them, so take the Legendre transform of the on-shell action with respect to the energy and angular momentum, okay, each of the 3 pieces in that equation, in that Legendre transform, is complicated, but they add up to something very beautiful, which is exactly what you would expect from the microscopics, from the extremo. So there's a beta mbps plus the bps entropy. Okay, that's the first point. And the second point is that this on-shell action can be written in this very nice way, can be written as a Legendre transform of the pre-potential at the poles, the sum of the 2 poles. Here again, you see this nice complexification. This equation should remind you of the beautiful formula of Cardoso, DeWitt, Mohaupt, and Capelli, and then the quantum version by Oguri, Strominger, and Waffa. We have the Legendre transform of the imaginary part of the pre-potential. But here there's a complexification. It's the pre-potential at the North Pole and the pre-potential bar at the South Pole. Okay, so there's something, so the solution automatically does this. Okay. So now I'll go to, those were the sort of key features. I'll go to the application to the heterotic ensemble. So the heterotic theory, we want to write it in this language. So we use string-string duality. So heterotic on T6 is type 2 on K3 times T2. So the pre-potential can be written in terms of the double intersection numbers of K3. So it looks like x1 over x0 times some quadratic form. And the 2 charges in this frame is 1 electric and 1 magnetic charge, okay, winding and momentum. And you can easily calculate the attractor, new attractor solution. And you get this. Okay, I've just written the scalars corresponding to these 2 charges, y and g. But now you notice that because this is 0, the heterotic dilaton, which is y1 over y0, blows up at the poles. Okay? So there's a potential singularity, and in fact, the interpretation is singular, that in the heterotic frame, the G string, so the sign of this is such that G string goes to 0. It's a funny singularity. The Einstein frame metric is perfectly smooth, okay? But at the tips and the poles, G string actually goes to 0. But that means that the string frame metric is singular. Right? And as an aside, the same conclusions can be reached So here I've used this n equal to supergravity formalism, but it can also be reached by just taking 10-dimensional heterotic string theory and compactifying on a torus. This was analyzed by Ashok in some papers 20 years ago. So that formalism also leads to the same conclusions. And in fact, we did that in one chapter of the paper, but we'll also hear, hopefully we'll also hear about this in Ashok's talk later this afternoon. Email.
Why wouldn't we expect this to be the sort of pathology that would be resolved within perturbative strings?
We do. That's the next point. Yeah. Okay. So in fact, let me make a comment here. So in the extremal case, when you write the solution, there's a manifest singularity, the horizon top of the thing, and then you need higher derivative corrections. So when we started this, our hope was that because you add rotation, things smoothen out. That this solution would be smooth. That was our hope, and it almost bore out, except that this dilaton is a problem, and so you actually do have to appeal to higher derivative correction. So that's exactly what the next topic is. Okay, so in string, if this is what you mean, let me say what I mean, and then maybe you can ask again if it's not clear. Okay, so I'm going to include higher derivative corrections, and one advantage of this formalism that I'm using, the n equal to 2 supergravity formalism, that a class of corrections can be analyzed with some work. At least the formalism allows for it systematically. Okay. So way to do that is, in addition to these scalars, you include another scalar, which is called upsilon, which is the square of the Weyl tensor. So it's a 4-derivative term, and you include that. So that's also a holomorphic superfield. And the first correction looks something like this. It's upsilon times y1 over y0, and c is some parameter I put, which is equal to 1. I'll just put that to track the higher derivative correction. And then there are further, this is 4 derivatives, and then the higher derivatives. And of course, the problem is, again, harder, but the formalism allows you to use supersymmetry, so it makes it slightly easier. And in some heroic work, the full supersymmetry equations were analyzed. If you had ADS2 symmetry, this would have simplified a lot. But in fact, these people give us the full equations. The solutions are hard, but what we found with Yiming and Joaquin is that, again, near the poles, these equations simplify. They become algebraic equations as if it were extremal. And now you see that you get non-zero contributions to the scalars. Okay, so C tells you that it's there. Okay, so now the dilaton is non-singular. George. No. C is just 1. I'm just showing, I'm putting C to tell you where it appears. C is 1. Yeah, I'll come to that in a second. First, let me just describe this. Here, I just want to say, you could ignore C, but then I would have to go to the previous slide to show that there's 0. This C just tells that. I'll come to the point in a second. Okay. All right, so that's the point of that. So dilaton is not singular. Now, in fact, not only do you not know, it should be obvious, because at 2 derivatives, the solution is singular. If you put a 4-derivative term, it's not singular. That means that those two are playing off. That means that any derivative also has the same effect. Okay, so this solution shouldn't be taken ultra seriously, but it's to show that it can remove the singularity, right, higher derivative effects. But there's a surprise to follow. Now we can try to calculate the action. Okay, this is a difficult problem. We haven't finished this. You can imagine this is some highly non-symmetric space, and you want to calculate some 4-derivative action. But this form of the action that we wrote doesn't suggest that it doesn't depend on the form of the exact forms of pre-potential and only uses supersymmetry. And if you take this form of the action, this Legendre transform, and evaluate it on this configuration that I just told you, you get exactly 4 pi square root of NW. This is the exactly the exponent of the microscopic theory, okay, of the index. Now you might think, so this looks like another miracle, but let's try to explain it a bit. Okay, so we have half an explanation. So remember that so if you have some supersymmetric compactification, the effective action can have all types of terms. Okay, they should all be supersymmetric invariants. Okay, and roughly speaking, in n equal to 2 theories, there are two types of invariants. Again, roughly like f terms and d terms of n equal to 1 theory. Okay, more precisely, they're in integrals over half superspace of holomorphic functions and full superspace integrals. Okay, so this formalism allows that, and that should take into account all kinds of corrections. Okay. The f-type terms are the ones which are captured by this prepotential, and they're also the ones which are captured by the topological string on the Calabi arm. Okay. Now, for K3, so these coefficients here are sort of these functions here can be calculated by the topological string, and for K3 times T2, because there's a zero mode on the T2, the topological string expansion terminates at one loop. Okay, so there are no higher corrections. So the f term prepotential is exact in this case. Okay? So that's sort of half the explanation, and of course there can still be all kinds of d terms. These are usually the not easy to calculate, but I want to point out that in a very similar problem for the case of extremal black holes, it was actually shown in these papers that d terms don't contribute to certain observables of this type, to supersymmetric entropy. Okay, so that's the hope. That's where we're going with this. Okay, so I'm at the last slide. 1 minute, perfect. So let me summarize. So we defined what a gravitational index is, and showed that for this two-charge heterotic string, the gravitational index is captured by a certain non-extremal supersymmetric Euclidean black hole, complex black hole. Now, one comment about which I invite more comments is that if you go back to the original context in the more general non-supersymmetric theory, so the string black hole transition of this kind, or more general brane black hole transitions of Horowitz and Polchinski, those are really transitions. So if you take the string entropy versus energy is linear and the black hole is quadratic, and then near string scale where they meet, you expect some kind of a transition. This, what I'm describing, although it's inspired by the same philosophy, the details are slightly different, namely that you have an index which you expect should be the same, and now we're trying to actually calculate it from the gravitational regime. So it's more like a duality. There are two pictures that smoothly interpolate into each other. On another front, so this idea of calculating the index using a path integral in asymptotic flat space can be pushed. So this, what we did today, I showed you how to take into account a single supersymmetric black hole. But as we know, there are other supersymmetric configurations. There's multi-center black holes, all kinds of stuff. And the question is, how do we? Here was my comment about the formalism, that if you do a sort of Hilbert space formalism, all these configurations look like different sectors, because they're all extremal. You have to go to infinite length to reach any of them, the throats. But in this path integral, they're all different saddles of the same path integral. Okay? So this is some work in progress with Jan and Luca and Joaquin. And the hope is to include multi-centered configurations, describe wall crossing. And then another direction is, as I showed you, this formula, this semi-classical formula reminds you a lot of the OSV formula. So because we're using supersymmetry, the hope is that perhaps there's some localized path integral in asymptotic flat space, which actually gives the full quantum entropy, free energy. Thank you very much for your attention. So, sorry, can I just, I'm not sure I answered Emil's question fully. So there were two things you might have been referring to, either what I said or you were talking about sigma models. I don't know what you meant.
Well, it was, yeah, sigma model might be one way of approaching it. You were talking, yeah. What if it was different? All right. Yeah, so one might think of approaching it from a sigma model point of view. I guess the particular higher derivative term you're interested in comes as some sort of alpha prime correction to the beta function equations.
Exactly, yeah. So you can take this effective, so here we took this effective field theory plus corrections, although it's not quite effective because of the question over there.
Well, one reason I was asking was that there are other examples where I'm thinking particularly of situations involving 5 branes, where it's even worse, right? It's a strong coupling singularity.
Yes.
And there we know that you know, there's situations where it looks like the supergravity solution has some horribly pathological strong coupling singularity, and yet perturbative string theory is perfectly fine.
Yeah, so one could, so that comment of yours I interpret as asking about the possible existence of some worldsheet theory with this target space. That's a very interesting question. Yeah, I don't know. I don't have an answer to that.
I actually want to follow up on Emil's question. Yeah. So you're describing the type 2A. In the type 2A side, it's a Riemann flux background. So, right? I mean, when you the worldsheet description of that is a bit non-trivial.
Yes.
And if you pass to the heterotic description, that's a string loop effect. So the data will blow up in the heterotic description, but presumably the worldsheet CFT is still somehow problematic, but the mechanism for resolution singularity will be due to a string loop effect, right?
No, not in the heterotic frame. In the heterotic frame, we expect it's all tree level. So remember, G string goes to 0.
I understand, but the alpha prime correction on type 2A isn't that?
Yeah, so in the heterotic frame, these are all tree level. We say alpha prime is really the
I thought. Sorry, I thought in type 2A it was tree level, no? That was, oh.
No, so this was the analysis of Ashok. I don't know if Ashok is here. Yeah. Maybe you want to comment, you'll say it better. No, so in the heterotic frame, this is completely tree level. So this was the scaling analysis that was done. Then
the worldsheet description would be, you'll just have some CFT.
That's the hope. That's exactly what, but I don't know how to write it, but there's a possibility that one could write that.
Oh, I just wanted to ask if there are also additional parameters you can add, like in the ADS5 case, where you don't just go to pi I, but there are additional free parameters.
Good. So this was my comment. So remember that in this, so start with let's say pure supergravity. In pure supergravity, there's nothing else. There's only spin. But in fact, even in these models, there are only gauge charges. So the only fields of the effective theory are these vector fields, and there's no sort of additional gauge field like you have in the gauge supergravity. There's no gauging. So the only thing that carries R charge is the spin. Okay. You can try to refine this with the gauge, with charges with the gauge, with gauge charges, with chemical potentials for that. And you have to be careful about duality and so on. But it's very different from the ADS5 case you're referring to, where you have different potentials already in the index. Okay, so here the index is this helicity supertrace. And there's lots of fermion modes, they get absorbed and you just get a number.
Is there one more question before the break? No, okay, so we'll have a coffee break now. We'll return at 11, and let's thank Sameer again.
Thank you.